This is lecture 15 on a series on a course on single agent search. And in this lecture, in this video, we're going to change topics a little bit. The last few videos were on suboptimal search, and now we're going to start looking at bidirectional search. And bidirectional search is an interesting topic because it dates back quite a long time, but it's only recently that we've started to have perhaps a more full understanding of what is going on in bidirectional search. So let's take a look at bidirectional search, and we'll have I think we're going to do two lectures here, two videos that are going to cover bidirectional search. And so let's just start out. What is the premise of bidirectional search? And the premise of bidirectional search is that we're going to have, if we have a start state and a goal state, and particularly if we think about a brute force search, then what might you expect to happen? And let me move these over just to get a little bit more space here. So what we might expect to happen is we think about, especially without a heuristic, we search out to some frontier, going from the start to the goal, and we have to do all the nodes within that frontier. And we could say, well, maybe if I'm able to do this, of course you can't do this in all state spaces, but maybe if I'm able to do this, then I could search forward and backwards at the same time. And if I'm doing that, I might get lucky, and I might only have to do two smaller searches here. And so we could ask, well, what is the potential gain of doing this in practice? And we can compute this, and it's going to depend on the type of state space that we have. So for instance, suppose that we have a polynomial state space where the number of states expanded is simply equal to the area of that's expanded here. And so we sort of assume that that area is somehow uniformly filled, and the costs are representative of sort of the straight distance cost to get to any particular node. So we'd expect here in a polynomial domain, let's just say it's two-dimensional, that there's going to be r squared states at some distance r. And for the sake of simplicity, we can just call this r. So there'd be r squared states in the, and actually here pi r squared, right? But basically r squared states in this area that we're expanding here. And when we think about a bidirectional search, what are we doing? Well, we're going to be doing a smaller search, which is pi, but now r is r over 2, so r over 2 squared. And we're going to have that for each of these, so we're going to have two of these. And so what we'd see here is that it's pi r squared over 2. Okay. So assuming that this is a circle, and of course that's not necessarily a perfect assumption, but assuming something like this, we could see that maybe in a polynomial domain, we could reduce the expansions by a factor of 2 by doing a bidirectional search. In an exponential search, though, then we have a very different picture. So here we're going to see b to the d states expanded. And over here, what we'd see is 2 times b to the d over 2. Okay. And it's very important to understand this. B to the d over 2 is much, much smaller than b to the d. So for instance, if I have b equals 2 and d is equal to 10, sorry, let's do 20 here. Okay, then this is about, then this would be about 1 million nodes. And if we go over here, then again, b is 2, d is equal to 20, but now I'm doing 20 divided by 10. 2 to the 10th is 1,024, times 2 is about 2,048 nodes. Okay, so if I'm in an exponential search and I am able to get this sort of gain where I take, branching factor b stays the same, I take the depth from depth 20 to depth 10, then I'm looking at several orders of magnitude of improvement by going from a brute force search to a brute force unidirectional search to a brute force bidirectional search. So this is the premise, and it seems sort of obvious that bidirectional search should be helping out here, but it ends up that in practice this hasn't always been the case. And so we're going to look in this video, we're going to look primarily at some of the theoretical background that is going to help us understand what is going on here. But let's first look at the unidirectional case. So let's look at here, we're going to call A star. And A star is an optimal unidirectional algorithm when given a consistent heuristic. And so what we see, if we look historically, we started with Dijkstra in 1959. Okay. And so I just have to reorder these slightly, sorry. So Dijkstra's algorithm came in 1959, which is like A star, but no heuristics, right? And then in 1966, we got our first bidirectional search algorithms. Okay, so those are over 50 years old now. And in 1968 is when we got A star. So our first unidirectional informed search algorithms. And it ends up in 1969. We got the name of this, but basically bidirectional heuristic search. I'll talk about these in just a second. And so we're continuing from there. So very early on, we see Dijkstra being taken from unidirectional to bidirectional search. Then we see heuristic search, and heuristic search very quickly goes from unidirectional heuristic search to bidirectional heuristic search. And then just to point out here is what we see is, although 1968 was A star, sort of the seminal work on the theory of A star comes in 1985. So this is a journal paper by Rena Dechter and Jutta Perl, and this goes into quite a lot of depth. I mean, there is some theoretical work inside the A star paper, but the 1985 paper really analyzes in complete depth what is going on between the theory. So we see this gap here between 1968 and 1985, where we went from having an algorithm to having the complete theory of that algorithm. And there's basically a similar gap between 1969 and I believe it's 2018 when we got our bidirectional heuristic search theory. So I'm going to cover some of that today, as I said. Now we want to talk about, so this is some of our history here. There are several different kinds of searches that we might be doing. And so let's just talk about some definitions of types of bidirectional search. Okay. And what we see is that there's two primary types of bidirectional search, and they have to do with where we're computing our particular heuristic search, where we're computing our heuristics. Okay, so if I'm just doing a brute force search, I do a brute force search, I just expand states on either side, and that's fairly straightforward. But here we're going to think about two types of bidirectional search. One of them is front to end, and the other one is front to front. Okay, and in this lecture, I'm going to primarily talk about the front to end heuristics. It's a little bit easier to describe, but we will get into a little bit of the front to front cases. So what is a front to end heuristic? Well, the idea is I have my start and my goal, and I'm starting to search out here, I'm starting to search out here. And the question is, when I evaluate a state on the frontier, where do I evaluate that state? If it's front to end, then I'm evaluating that state with respect to the goal in the other direction. If it's front to front, then what am I doing? I'm actually evaluating this state with respect to the other frontier. Now, if I look at this case, obviously, I have to have a heuristic that I can look up between any particular state on the frontier to be able to do a front-to-front algorithm. Whereas here, I only have to look up the heuristic with respect to one goal state. So this looks like it'd be much simpler to implement in practice, or will apply to a broader number of domains. But there's a secondary issue here that is present, and that what that is that when I look at this search here, there's actually many possible states on the frontier. And so when we think about front-to-front search, we tend to have a problem of sort of this n squared heuristics computations, because I can look up this heuristic with respect to every state on the frontier. And unless we can handle that efficiently, that on its own is going to make front-to-front search fairly inaccurate. Now, there is a specialized algorithm here, which we're not going to talk about, but it's called single frontier bidirectional search. And this is an algorithm that does not handle the case of this n-squared lookups. It actually creates pairs of states. And so you sort of get an n-squared overhead in states in the frontier because it's using a single frontier and sort of representing pairs of states that you're trying to connect together. This can still be a very effective algorithm because the one advantage we have here is that when we have a heuristic that's estimating over a longer distance, that heuristic tends to be inaccurate. When we have a heuristic that's estimating over a smaller distance, it's going to tend to be more accurate. And so the heuristics we can get between frontiers here are going to tend to be more accurate and then cause us to do less work. Okay, so for right now, we're just going to look at the front-to-end case then, and we're going to see what we can learn from the front-to-end case of bidirectional search. And so what we find is that in 1969, and so interesting here, the bidirectional heuristic search was done by Pohl. So we'll relook at this history here as another piece of bidirectional algorithms. So 1969 was the very general heuristic algorithm. And so this is by Pohl. Pohl in 1970 gave us suboptimal search, gave us weighted A star. And so he was doing some very important work at the foundation of the field back in the late 60s and early 70s. And so this is part of his PhD thesis. And a fundamental thing that was showing up here is, well, it looks like this should be a really good thing to do. We add heuristics, we do really well. We know we can add bidirectional search, we can do really well. Why don't we add them all together? And in his thesis, it didn't really work very well. And there weren't very good explanations at the time. And so historically, I'm going to point out a couple pieces of work that were trying to understand what was going on. And so what we see in 1989, there was an algorithm called BS star by Qua. And this algorithm was looking at the frontiers. It ends up that it was very possible in previous algorithms that the two search frontiers could actually not only hit each other, but cross. And so BS star put a number of enhancements in that tried to avoid having the frontiers cross. And that was an important thing. You don't necessarily want that to happen, but it didn't necessarily give us the performance that we wanted in bidirectional search. So people worked on this problem of how maybe we can improve this. And so in 1997, there was a series of papers around here. In particular, we see some work by Kindle and Kynes. And when I was doing work, this was sort of, this is around the time I was doing my PhD. The explanation was, well, we're just spending too much time proving the optimal solution. So maybe we have two frontiers, they're searching, they meet very early, but then they have to do a whole bunch of work to prove that they've actually found the optimal solution. So this is sort of the operative explanation of bidirectional search and why it wasn't working well. And we have to go forward now another 18 years to 2015, which was a conjecture that came from Barker and Korf. And so Korf, again, is the one who gave us IDA star, is basically the conjecture is that we should never do bidirectional search. Bidirectional heuristic search. And just to say that's a conjecture. And there were a number of pieces in this conjecture that were coming up with this explanation. They were looking at the impact of a heuristic, and they were making an informal argument on this and basically saying, look, if the heuristic is really strong, then a unidirectional search is just going to get us straight to the goal. And if the heuristic is weak, then although it might be in general, it might help a little bit, but it's not going to be helpful in the places that we need it. and therefore in a week with a weaker heuristic, then you might as well just use a brute force search. You shouldn't really be using a informed search algorithm. But there were some assumptions in here. For instance, they assumed that the two algorithms searched and met in the middle of the search. And so those conjectures are not necessarily guaranteed to be true. And so in 2016, there was work by, the primary work here was done by Rob Holtze. And here, there's a new algorithm developed called MM. And MM, the idea here is that we could meet in the middle. And so this is the first algorithm that actually was able to meet in the middle. And that's a guarantee that the two search frontiers, one, won't cross. So that's addressing the problem of BS star. We are guaranteed, in fact, there's a general version of this called FMM, where you can say, look, I'm going to meet anywhere that I want on the frontier. I can choose the fractional point where I'm going to meet. And so has the potential to work really well. And we're not going to be having to do lots of extra states as we're doing this. And so this is always being able to meet in the middle. And the other thing here is better termination. It ends up that in bidirectional search, termination is something that's really hard to get right. And there is actually an algorithm before 1966 that was looking at termination conditions and didn't quite get them right. And so 1966 was the first time that they were done correctly. So this is 50 years after that first work. And so we see that there. And I'll talk briefly about the meet in the middle algorithm because it's interesting. But when we actually define the theory, what we can find, and I don't think I'll have time in these videos to go through all the detail, but we can actually find that the meet in the middle algorithm is still in some ways deficient because we were lacking in all of this a theory. So if we look up here, we see, A star as an algorithm in 1968, and the theory didn't come until 1985. If we look here, we start to have algorithms in 1969, but we didn't get any theory in 1985. And in fact, the first theory that we get was starting around 2017. I think this is in the summer of 2017. So we'll look at the theory. And actually, some of this theory had been published in a thesis in German, quite a few, like in the 1990s, but it was in German. It had never been published outside of that thesis, and the results were not completely known or not well known by the community. And the results were only for front-to-front search. And so this theory work that appeared here was able to generalize this or write this down both for front-to-front algorithms and front-to-end algorithms and package this all together. So what we see here is for the bidirectional search, there's been a really big gap between when the theory was developed and all the other algorithms that were developed up until that point. And this is somewhat problematic because it ends up that, as I said, the bidirectional theory is a little bit more complicated. And so if we don't have the theory right, then it means that our algorithms probably aren't right either. And we'll see a little bit about that. So in order to understand this, so we've got our history down here. In order to understand this, what we're going to want to do is to start to look at the theory. We'll start with the theory of A star. Okay, so what is the A star theory? And the way to think about this, I believe this was in an earlier lecture, but when I think about is what states, so if I give you, because the theory is a little bit funny sometimes for practical problems, but you can think about this is if we give you a solution with cost C star, what nodes do we have to expand to prove optimality? Okay. What states do we have to expand to prove optimality? And so, of course, we can use this to guide a search algorithm, but we can also think about this proof. And so what we know for A star This is a simple version. As I said, the 1985 paper has a complete and full theory of this. We know that any state that has f of n less than c star must be expanded. And if we don't expand those states, then we might be missing a solution, and we might not have actually proven that this is the optimal solution. And where does this come from? So what this comes from is this picture of a start state. And then we have some search that's going on. We have a closed list. And then we have nodes that are on the frontier. We'll just say that node U is on the frontier. And then we have some potential path here to the goal. And so this is the picture that we're drawing of our expansions. And we're saying, look, we already know that we've come from start to U. We know we've come from start to U optimally because of the consistent heuristic and other properties like that. And then I've got a heuristic that is giving me then the complete estimate of the cost of a state. So right, I have the actual path plus the heuristic. This is giving me a bound on the total path length between the start and the goal. And that's where we're getting the A star picture. Now, I want to say here, now that we're done with the A star theory, so that's all we need of the A star theory, that there is a really nice demo, or of course I think it's nice, but there's a little game I made that's on the Moving AI site. The link is should be down below, and it's a game for looking at the necessary expansions for A star and comparing them to bidirectional search. And so it's a game where you can take a problem, you can choose a start and a goal, you can choose a state that you think is necessarily expanded by A star, and then you can play around with it, and then you can try and see if you can think about what are states that might be necessarily expanded by bidirectional search. And we're going to go ahead here and start to look at this picture. So bidirectional search. And the key for bidirectional search is that we have a very different picture here of what is going on in a bidirectional search, because here we have two frontiers. We've got the start. We've got to search out to some U that's on the frontier, but we also have a goal, and we have a frontier here going out from the goal. So if we think about the frontiers in both going out in the forward direction, going out the backwards direction, now when we think about paths, there's actually quite a few more paths. So over here on the right-hand side with this picture, right, for a certain node U, there is the path to U, and then from U, there's the path to the goal, and that's about all that we can do. But we look at this bidirectional picture, and we're going to, again, use a front-end heuristic. What we have is, well, we can go from S to U, and then once we've done that, we can think about U going directly to the goal. We could also think about going from S to U and U going to V, and then V going to the goal. And we could also think about the path going from S to V and then V to the goal. Or we can think about this in the backwards direction, the path to V and then trying to traverse backwards from V back to the start state. Okay, so we have many more pictures here. And with these many more pictures, I'm going to get a more complicated understanding of what is going on and what are the possible things that can happen. And so in bidirectional search, then what we have is we're going to get several different conditions here. And let's go ahead and write these down. So on the right-hand side, we just had f of n less than c star. On the right-hand side, what do we have? So the first thing we could get is f of u is less than c star. And that's going to be just the normal condition we got here. So, and I'm going to write f here to say it's in the forward condition. I also can get in the backwards direction. So I could say f in the backwards direction of v would also have to be less than c star. Because what I want to basically prove, if I think about states that are existing here, I want to say, well, do I have to expand u? Or in bidirectional search, we're going to be thinking not only about this state, but also about states over here. And we'll actually be thinking about all the states, pairs of states in the frontier, but we can do this a little bit implicitly. Or there's efficient ways that we can do it. So I've got a U here, I've got a V. As I said, the path can go from U to the goal, which gives us this condition. And the path from V can go to S, which will give us this condition. And then the last thing that we have is we could be actually meeting the frontier. So what we could have is G forward, which is basically this forward cost to get to U, and then we have the cost to get to V, and G forward of U plus G backwards of V is less than C star. And well, all of these things are giving us bounds. So actually, I'm going to remove the less than C star for right here. What we see is all of these are giving us bounds on the solution. And this is a solution from U and V. And so these are all possible ways we can do this. So if we want to write out a theory of this, then what we're going to talk about is all of these are possible. And all of these are estimates of the cost of getting a path from the start to the goal going through some nodes U and V. So over here, we only had to consider U. Now we're going to have to consider both U and V in our frontier. There could be many different V's, and so I might have to, of course, consider all U's and V's, all such pairs. And what am I going to get? So what we're going to do is we're going to define LB, LB min, just LB, to of a pair of states. And this is going to be equal to the maximum of F forward of U, of F backwards of V, and of G forward of U plus G backwards of V. Okay. So that's our lower bound calculation. And what we can say is if the lower bound of UV is less than C star, we must expand something. Now, what must we expand? Well, this is a little bit more tricky. In A star, I just say I have to expand U. But in a bidirectional search, we have to expand either U or V. And the reasoning here is that, well, I could just continue the search forward until I prove that I don't have to expand V, or I could go backwards, or I could, of course, do them both together. So we must expand either U or V. And this is probably the reason why it took so many years for bidirectional search to be developed, or for the theory to be developed, because there's such simple conditions here. I have to expand all states with F of U less than the goal for unidirectional search, and that's the set, and you must expand them. But when you look at bidirectional search, I'm going to get an or statement in here, either U or V, because I can go in the forward direction, I can go in the backwards direction. And if you want to understand this more, what I recommend is go play the game that's in the link. And there's basically an oracle inside the game, that's going to help you understand why this is the case. And so there's some challenges that the game gives you to help you understand this case of why it is either U or V that we have to expand. But as I said, then this gives us conditions for expanding any pair of states. Now, on our two frontiers, there could be sort of this number of nodes, the number of pairs that we're thinking about is squared. You know, if I have n nodes on each side, then it's n squared pairs that I have to think about. But it is possible to build algorithms, even in the front-to-end case, that don't think about all of these squared pairs. So we can do some of this a little bit more efficiently. And so what I'm going to do is I'm going to stop this lecture here, because this video here, because this gives us the bounds. And what we'll do is we'll look at the implications of these bounds. What is the implication of this being an OR statement here in the next video?